Oh, sorry. Okay. Today we need to recall the Lewis structure. You remember that we learned how to make the Lewis structure and bond and how they share the electron between them to fulfill the octet theory and the duet theory. Correct? We will apply this knowledge and we will move on for this chapter. So this chapter may name molecular geometry, topic 10. But we will be discussing here three things: formal charge and resonance structure, exceptions to octet rule, and VSPR theory, and determining geometry. This third topic and the 11th topic will have so many correlations. So we also saw the here the non-polar share bond electrons between two atoms that go equal distribution of electron, but there are some polar covalent bond. The electron distribution is not equal, and you will see that some places has the zero charge, some places you will see the negative charge. Especially the polyatomic ions are interestingly follow this type on the basis of the covalent bonding, and here the unequal electron distribution or bond grouping or something like that. That today we are going to see and how we can calculate. This is also recall your Lewis structure review. You remember the S equal to N divided by A. N is the how many possible octet structure, atom we have, and then we have to subtract the valence electron. Then finally we will find the bonding electron, correct? So we will use this knowledge and then we will move on. So fill in the remaining bonding line. Satisfy the duet or octet rule using the remaining electron. Bond length or bond strength. You guys remember that when the single bond, double bond, triple bond, triple bond is more strong, stable than the double bond, right? Double bond is more stable than the single bond. Also, we check it out the length. Correct? Single bond length was more high, and the number of bond increasing, length is shortening, but stability and power is increasing. So we will also see today some this type of things here today. So by this knowledge we already learned. So we will move on. It is also possible. We have seen that one covalent bond makes one Lewis structure. Correct? But today we will be observed that one compound, one covalent compound, but we can make more than one Lewis structure. And there the term resonance and formal charge. So if I want to describe you resonance, I will first show you the example. However, resonance are the kind of things like nitrogen. Let's first move on the example. We will come back here. Yeah, look into here. The Lewis structure of nitrogen peroxide. Sorry, this is not the peroxide actually. This is NO2 and this one. You know, nitrate and nitrite. This is the nitrite one, NO2, negative charge one, polyatomic ion. So here you could see the nitrogen valency. You remember, can you tell the valence electron of nitrogen? Atomic number is 7. So how many it will be have valence electron? Nitrogen, N. Yes. And oxygen? 6, huh? Yes. Oxygen 6. So now if you look into here, so we have 2 oxygen and 1 nitrogen, correct? So when we are drawing the Lewis structure, this both structure is correct. That means electron share and making a bond with nitrogen, those electron location can be switched, can be changed, the location or direction. Did you see? Left side and right side, huh? This is the variation or vibration of the electron that make a bond by sharing during the formation of covalent bond. And these vibrations and this switching or this character, we say the resonance. And today we will check it out, the details of that, why and how it happens, and how we can find that why this is the minus charge, why somebody at the different charge. So that's today we are going to learn here first. So we can draw more than one valid Lewis structure for many molecules with double or triple bond. Resonance structures are valid Lewis configuration with the same atomic scaffold. That means the NO2 is same, but if you see the difference, just one difference, that the for one Lewis structure, the left side oxygen make a double bond with the nitrogen, and for the right side structure, right side oxygen make the bond, we share and make the bond with the nitrogen. Correct? So that means electron can share either this side or this side. So this is possible. This is the resonance. But if you look into the chemical structure or atomic scaffold, these two are same, NO2, correct? And overall the charge -1, correct? So that's we are going to see that how it, why it happening and how it happening, and we can totally quantitatively calculate and prove these things. All resonance structures contribute to the overall actual structures of a molecule, but not always equally. That we show our principle is here. The not equal sharing, because you know, this is also kind of things that you will see most of the polyatomic ion which have the valency electron even and odd. That time this type of situation comes. I mean, this is my just experience. Any question? So let's move on. First, let's as an example that how we can write the resonance structure of nitride that I say. So first we will see the how many bonds or bonding in total electrons and how many bonds we can make. So let's look into here. So S equal to N minus A. I just want to review. If you forget, it will be a review for you. So we have 1 nitrogen and 2 oxygen. So we need either octet or duet. But duet is exceptional for the hydrogen or something, correct? But here, for the oxygen and for the nitrogen, we need octet. We know the nitrogen valency electron is 5 and oxygen valency electron 6. So we have total 3 atoms, 2 oxygen, 1 nitrogen. That's why 3 times 8, N. And minus A, valence electron for the nitrogen 5, and oxygen 2 times 6. Also, you remember the what does it mean, the negative ion? Negative ion 1 means they accept 1 electron from something, correct? Because we know when metal donates the electron, they get the positive ion. And when non-metal takes the electron, they get the negative ion. So here, that's why we need to add 1 more electron here. So that means finally we have 24 minus 18, 6. We know that 1 bond or 1 line equal to 2 electrons, correct? So total 3 bonds we can make. I hope you guys have now nice review on that. Let's move on. So when we make this, I think I draw somewhere. Yeah, here we go. I will little bit of draw here. What actually happened and why we do like that and why both are correct. Go back to the blackboard. So we are talking about the nitrogen nitride, NO2 negative 1 charge. So we can write the 2 types of Lewis structure. So it can be like that. Okay, I will put little bit of valence electron also. And we can also make like this way. Like that. Now, if we consider the now electron 2, 4, 6, and 2, 8. Here we have, because here is a 4 and here is a 1. So we have one lone pair here. So here is a 2 electron, correct? 2 plus 2, here is actually 1, we have lone pair. So here similarly we have here 2, 2, 4. And also 2 electron here, that already make a bond with here, sharing. Now the thing is that if you look into now here and here, what we are find? 2, 2, 4, 2, 6, and share 2 here, the 8, octet, correct? In that case, we have here the 2 here, here is a 2, and here is 1. But still we need more 2. That's why they make the double bond either this way and this way. So actually what happened? The scene is like that. If I show you this one by double bond, so what happened actually? So actually like that. Let's change the color. So this 4 dot equal to actually the double bond, correct? 4 electron. So then, oh sorry, this will be O, okay? So then if we have a 4 here, oxygen, so how many more we have? We have here we go 2 and here we go 2. You can write here or here, anyway. So this is how the double bond and electron are using sharing to make a bond, and finally we are getting the octet. Now the thing is that this side we have for the nitrogen, this side we have 2 electrons, single bond. This side we have 4 electrons, so 4 to 6 electron, and still we have here. So this is how we can show the bond here. Now let's clean this board and let's write about the formal charge, why this is -1. So first go back to your file. Sorry. Okay, so this is how, according to make the octet, we can make like that the distribution of electron. Now the structure predict to different NO bond length. Experimentally, we find that there is only one bond length. The bond order is halfway. That you will not understand until I will show you the charts. So now let's see resonance structure of nitride. Oh, by the way, I wanted to show you something here. So these two possible Lewis structure we can write. However, if we now ask me, if you ask me, then if I ask to write one structure of NO2, how we are going to write? So the real molecule then represented by the hybrid structure like that. This dot represents that this bond can be made either this way or either this way oxygen. Got it? This is how we represent. Now the most important things, consider the formal charge. So how we can calculate the formal charge? I will give you another counting. When we will do this one, it can be easy. Similar procedure, but I have little still forward way, so I'm going back there. So how we can calculate the formal charge? So rule is like that. Formal charge. Formal charge means the the negative sign. Most of the polyatomic anion have in nitrate, sulfate, phosphate. We have -2, -3. This is called the formal charge. So how we calculate this formal charge and from where actually it comes? Because all are mostly the covalent compound. So we can calculate, this is kind of mathematics. So formal charge equal to valency electron. You guys can note it down, it will be helpful. So please do not mind writing, it's very difficult mouse writing. So for valency electron, for each atom minus non-bonding electron. Electron minus bonding electron divided by 2. So the electron they share and make a bond, because share electron have both the atoms contribution, correct? 2 atoms contribution. That's why minus bonding electron this is electron, okay? Bonding electron divided by 2. So now let's write for the this one. So oxygen valency electron, these are the bonding electron. Here we have double bond, so 4. We can calculate both sides, but any kind of way we can write and calculate, so it's okay. And then we have oxygen, so another 4. Now let's calculate how we can do for the left oxygen atom. Okay, first we will do this left oxygen atom, calculate. How many valency electron we have? 2, 4, 6, correct? So let's write first here. Minus. How many non-bonding electron we have? Non-bonding means which didn't participate in making a bond. Okay, so it is still 6, correct? Minus 6. Now minus how many bonding electron we have? We have 2 electron here, correct? Because this oxygen make a bond with the nitrogen, huh? And when one bond is made, one bond or one line equal to 2 electrons, correct? So we will write the 2. This one, I'm talking about this one. So 2 divided by 2. This is our rules calculation. So that fixed. So now let's see left electron what giving. This 6 plus 6 minus 6, 0. This nullify 1. So 0 minus 1 equal to minus 1 charge. So this charge we write on the parenthesis. Now got it? The polyatomic ion charge, how it comes? So this charge, this is for the left oxygen. Now let's calculate for the right oxygen. In that case, right is this oxygen. So right side oxygen, valency electron, how many here? The same. We know this is 6 electron. How many non-bonding electron here? Here is not the same here, because here double bond, correct? More participation for making bond. So here the non-bonding electron will be these 2 and these 2. You guys are clear about it here? So then we will have to write 4. Now can you tell in case of right how many electron participate in making bond? 4 electron here, correct? So we have to write the 4 bonding electron divided by 2. Then what is coming here? 6 minus 4 equal to 2, and 2. So 2 minus 2 equal to 0. Got it? 0 we don't need to write. If you have a question, let me know first. Because if we clear one, then we can do all the practice. So we have to know which are bonding and non-bonding electrons. Non-bonding means already the electron that doesn't participate in making the covalent bond with central atom. Got it? Here central atom is nitrogen, correct? So in the left oxygen, if we see and the purpose is octet. So if we look into the left electron, 2 electrons make a bond with the nitrogen and we have 6 more dots, correct? So 6 plus 2 octet, because we know when there will be octet, that means this is the covalent bond established, correct? In the center atom nitrogen have 2 and then make 2 with the oxygen, 2 to 4, and nitrogen make double bond, 4 electrons with oxygen. So this is how nitrogen is also octet, correct? Right side, 4 electron of right side oxygen making the double bond with the nitrogen, and we have 4 more electrons. So the 4 more electrons, they didn't make any bond with the central atom. This is called the non-bonding electron. Got it? And valency electrons means the single atom's total valency. That we find from the periodic table, correct? Or drawing the electronic configuration. Now you guys got it? Guys, you guys got it? Yeah, let's then move on. Then for the nitrogen. Center atom, nitrogen. So we know the nitrogen valency electron is 5. Here the non-bonding electron is 2, these two. So 2, and bonding electron how many? 6. Here is a 4, here is a 2. So 6 divided by 2. So it's coming 3 minus 3. See, 3 times 2 equal to 6, so equal to 0. So that's why the overall charge of this ion we can write like that. Now you guys got it? And this is called the formal charge, and this is the easiest way and very clear-cut way to calculate the formal charge. Now you can calculate any other ion formal charge. We will do it in some more practice here. Otherwise, yeah. I think I have some. Okay. So now I think you got it. Your lecture have the similar thing, but in the lecture you have the writing the sentence, but here kind of mathematics. So I think this one I find in other books and also the internet, and similar thing. Rules are same, but I find this is equation is very straightforward. So I prefer this one. It will be recorded here, keep recorded here. So go back to shell file. When we draw Lewis structure, we distribute the total number of electrons over all atoms. This results in a redistribution of the charge. So formal charge equal to electrons it should have minus electron it does have. So valency, that's why I'm telling that does have means the non-bonding one, should have means the valency. So also the non-bonding, the bonding divided by 2. So that's why I find the easiest way that we calculated than you have here. So please remember and note it down that we follow. I didn't follow here because this is other way to find it. But what is the other way? They did the direct calculation, non-bonding and the bonding divided by 2. Got it? But I think that's more complicated for you guys, student. So the rule I give you, that's more clear-cut and easy. So follow this one. So now I think you know that how we got the -1, how we got the 0 and 0 here, correct? Yes. Let's do this one. What is the formal charge of the oxygen atom of the hydronium ion? So let's draw and make it. So in case of, do you know what is the H3O? Water, when we have the water, some water molecules partially dissociate and they make those dissociation hydrogen ion with the water molecule. So that makes the H3O and the hydronium ion. So let's make the structure here. So, okay, I need to ask you, I hope you didn't forget. Do you know how we choose the central atom during drawing the Lewis structure? So say yes. Huh? Yes. So which one will be least electronegative? That one will be central atom. Yeah. So here we have the oxygen central atom. So now the structure for that is like that. You know there is a duet rule because hydrogen is 1. So 3, 2, 6 and we have here 2. So now let's calculate the for first one hydrogen. And because they're asking for the oxygen, so if we calculate the one hydrogen and oxygen, we will find our result. So first do for hydrogen. So the valency electron equal to 1 minus bonding electron is also, do we have the non-bonding electron here? I don't think so. Yeah, non-bonding electron. In case of hydrogen, we don't have non-bonding because hydrogen have 1 and that already participate with oxygen. So that's why we will write like that. So 0, non-bonding 0, and also the 2, bonding here 2 divided by 2. So 1 minus 0 and 1. So that means actually 1 minus 0 minus 1 actually 0. It will finally come. Now here oxygen. We have the valence electron 6. We have the non-bonding electron 2. We have the bonding electron 2, 2, 2, 6 divided by 2. So then it comes 4 minus 3 equal to plus 1. So now you got it, the charge, how it comes. So this is how we have to calculate the formal charge. So this is the answer for that. So here the lone pair electron means the, here we go. Now we will talk about the bond order. What is the average bond order in the nitrate? So we now saw that how to calculate the formal charge and also resonance, how to draw the structure of resonance for the ions that might have more than one Lewis structure. We also saw that when we need to write the stable hybrid structure, how we should draw it. So with the dot, that this side and this side, any either side can be the double bond. We need to show. Now we will see that how we are going to calculate the average bond order in the nitrate or any other polyatomic anion. So let's consider, draw again here. So here NO3, correct? So here actually if we draw the formal charge, actually it will come here like that. -1, here the +1, and here the -1. So this +1, this -1 will be nullified. And one double bond will be 0. Oh, sorry, I did a little bit of mistake during the drawing. Just a minute. So, yeah, I did a little bit of mistake. So one double bond is here. Here this one. Here, now it's fine. That's why I could not match it. So there we have 0. Here we have +1. And here we have -1, and here we have the just a minute, I did again little mistake. Eraser. This is oxygen, correct? -1, +1. This is a 0 charge, and this is -1. Now, this you can also practice. So I'm not showing here. This plus, this minus, this plus will be nullified, and this minus charge will become here. You guys can practice when you guys will do. So you guys can write it down and check it out. Like here, we have the 2. So how many we have here? 2, 2, 2. Correct? 3 line. I mean, your presentation slide, you will see the line. Line means the 2 electron, like that. Like that. So you can do that. But my question to my things to show you, explain you how we can calculate the bond order. So what you have to learn here, that single bond, double bond, and triple bond. This is single bond. This is the double bond, and this is the triple bond. So when we will have this type of structure, we need to first draw, and we need to count that how many bonds we have. So if this is single bond, we will count 1 bond, okay? If this is double bond, we will count 2 bonds. If this is triple bond, we will count the 3 bonds. And then we need to first addition and then do average. Got it? So in that case then, how many we have? So we also have the rules here, the total bonds and the bond domain. So how we can do the total bond? You can also note it down here. This is also easy to calculate the bond order. So the total bond divided by bond domain. Domain means that this here is a how many? So nitrogen, oxygen, this type of. And total bond is here the 3 domain like nitrogen, oxygen. But total bond how many? Can anybody say how many total bond we have here? So 2 single bond and 2 double bond, correct? So we have the total bond 4. And bond domain, I told you that this is the central atom to atom. Bond domain. Yes.
Isn't it like 2 single bonds and 1 double bond?
Yeah, so two single bond, we will consider 2 plus 2 double bond 2. Oh. That's I was telling here that single bond equal to 1 bond, double bond equal to 2 bond, triple bond equal to 3 bond. So when we have to we have to calculate the bond order, we have to be add all the bond we have in the structure. So if you don't draw, you cannot find out that how many bond you have, correct? So in that case, you have 1 single bond, here is a 1 single bond, 2 plus, so like that, 1, let's make it more easier, 1 plus 2, so equal to 4. But domains, divided by domains means the central atom to atom bond. So that we will be calculating nitrogen to oxygen 1, this nitrogen to this oxygen 2, this nitrogen to this oxygen 3. So that means domain 3 but bond 4. Got it? So, so when we will calculate the domain, we will not consider the double bond, single bond, triple bond. That time, NO one domain. NO another, how many we have. But the number of bond, total bonds, that time we will calculate 1, 2, 4. But domain means here to here one bond, here to here one bond making, here to one. So that will become 3. So now if we put this value here, so 4, total bond 4 and the bond domain 3. Now if you divided 4 by 3, can anybody tell what will come?
1.33.
Yes, sir. So this is the answer. Got it? So for this calculation, you also don't need to be used here. The way I show you, that is enough for calculation. So please note it down and check your recorded lecture. So just write the equation, the total bonds divided by bond domain. And now I already explained that how you will calculate. Total bond means here we have one single bond, and one double bond. So 1 plus 1 double means 2. So 4. And domain means this one is one domain, this one is another domain, and this one is another domain. Now got it? Yes. So let's go for another one. But I think somewhere I took some more examples. Okay, let's move on here first. A student in general chemistry has been asked to draw all the possible resonance structure for this ion. This is called mesylate anion. The student has proposed the following 4. Which of the Lewis structure proposed by a student is the most stable resonance structure? So let's see here. If we consider here 5 unit formal charge, here is a 2, here is a sulfur. This is this plus 2 for the sulfur. This oxygen have the negative 1. Here we have. But total 5 unit formal charge, but some will be nullified. Anyway, let's go. This is not a resonance. Resonance means when we have the possibility to make the charge in different way. But here it seems the structured hydrogen atoms has moved. How? This hydrogen atom moved here. Okay, let's move on. Octet rule violation. Octet rule violation. How the octet rule violation? 2 to 4. Okay, here the 2 to 4, 6, 8. I see, because carbon valence electron is not like that. Carbon valence electron is, do you remember what is the atomic number for the carbon? 6. Then carbon valence electron 4. Correct? Okay. 1 unit formal charge. Yeah. The reason here, now if we look into the explanation they want to give here, this question is little bit of tricky, but let's see that formal charge is -1. But if we look into here, the multiple formal charge, and this makes the is more not so much stable. Here they change the hydrogen, but in the resonance explanation, we learn that we don't change the atom. Got it? We don't change the atom. We just change the electron location of site to make a bond. So that's why this is also not the correct one. Here, for me, this one is the very clear that this doesn't follow the octet rule. But here, it seems that all are correct, and this one have the -1 formal charge. So that's why. And if you want to practice, you guys can little practice here, then how they draw the, you can calculate the formal charge also to make sure. Now we already know the octet and duet group. However, some we have the exception, and this exception where they are stable. That's I always tell that in the chemistry or science, you always find the normal things, rules maintain compound, but you will find the exception that doesn't maintain the rule, but still they are working and stable. So this is how here we have this compound BH3. So this BH3 actually the didn't make the octet, but they have the 6 here, but still they are stable, and this is the exception. So you have to remember, there is no way except remembering. Another one we have here. So here we have 12 electrons. It didn't follow the octet rule, because we know octet means 8, but if you look into those and count, you will see this type of different number of electrons, either less than 8 or more than 8. So what is the then things that we have to summarize? The exception, we usually make 3 bonds. Okay, so we don't have any option except we need to be remember those exception. And which are exception? Period 2 elements never exceed the octet rule. B usually makes 3 bonds. Period 3 and heavier elements often satisfy the octet rule but can exceed the octet rule by using their empty valency d orbital. So those are the example. Please remember those are the example 3. I mean, that's actually what you have. If you make a question, we will keep here. The final topic for this chapter is the electron geometry or BSPR theory. Valency shell electron pair repulsion. While Lewis structures accurately predict where electrons are located in a molecule, they do not tell you about the 3D geometry of a molecule. So we saw that how we can draw the Lewis structure, we learned first. We also saw that how we can calculate the bonding electron. Today we also learn lots of things, that how we can draw the resonance structure, that means more than one structure of same covalent enantiomer compound. We also saw how we can calculate the formal charge. We also saw that how we can calculate the bond length and number of bond, average number of bond. So last topic we have here, the VSEPR model. So Lewis structure can tell us lots, but still the limitations of Lewis structure is that Lewis structure cannot talk about the three-dimensional character of the molecules. So because, did you ever see the ball and stick that show the geometry of a chemistry, the way we write the structure? Okay. Ball and stick, sometimes if you have a too many chemistry courses, you guys can buy it, but actually you don't need. You guys can slowly, when you will go to the organic chemistry and more advanced. Yeah, if you need to take the 2 organic chemistry courses, then if you have the those type of hand tool, you can easily draw the set the three-dimensional structure. Anyway, so Lewis structure cannot deal with the or don't deal with the 3D structure. So valence shell electron repair pair repulsion, VSEPR, will be tell us lots of things about that. So electron geometry, apply the VSEPR rules for the bond and the lone pairs to find fast shape. I think last year there is a one laboratory course for the, in this department, General Chemistry 1 and 2 laboratory together. I took the course, I still remember. I think in my blackboard already have those experiments. So we have some software, free software that we can write the molecules structure, and they will show you that how the three-dimensional structure is coming and how we can predict the angle. That's from the linear different types of length angle that we are going to talk here. So, okay, so if I find, I can also show, I think, the next week. But anyway, so we can apply the electron geometry, VSPR rules for bond and lone pairs to find the first shape, and molecular geometry consider only bonded atoms to find the second shape. So let's see. First, we will talk about the electron geometry. Are you guys tired? Is okay? Yeah. Since we have a holiday on Monday, correct? Guys, remember Monday the college is closed, okay? My syllabus showing that still have a lecture class, but today we check out the next Monday, 20th June, correct? Is college closed, so that day we don't need to come here or we don't need to do any recitation or anything, okay? So, the electron geometry of a molecule, that is the arrangement of electron in space, is attained by minimizing the electron pair repulsion. So, put the electron groups as far apart as possible. Yeah, that's, I want to tell you something. Okay, let's go back to the structure. Okay, for example, here are represent the copper hexachloride, the chlorine and copper, and now the electron have in some space. So if you see here to here, here to here, and here to here. So if these two atoms are far enough, that means the electron between these two will not repel each other. So we can avoid those problems. But if they are very close, so they will, that means they will repulse or repulsion will happen. So that they are telling here that by minimizing electron pair repulsion, put the electron groups as far apart as possible. What count as an electron group? One lone pair electron is one electron group. Two electron in a single bond equal to one electron group. 4 electrons in a double bond is also equal to 1 electron group. 6 electron in triple bond, also 1 electron group. So that means it doesn't matter how the, let's consider A, let's consider the double bond B, let's consider the double bond C. It doesn't matter the bond, they bonded by single, double or triple, each we will consider as a 1 electron group. Got it? So we have to make sure and to draw the three-dimensional structure or make the things like that, the electron in space, so that between the two electron groups, if they come together, then they will not be stable too much. These things, you have too much detail in the organic chemistry first, second. If you have to take the hydrocarbon, methane, ethane, that time you have to detail. Like I teach the spring semester, I taught organic chemistry 1 and 2 in St. John's University. There was a lot of this type of mechanism. Anyway, so now comes to the molecular geometry. Covalent compounds have definite shapes that can be accurately predicted. This is a two-step process. First, Lewis structure, valency electron arrangement, and then valency shell electron pair repulsion, that means 3D structure. So molecular geometry, we need both Lewis structure and the VSEPR 3D structure. Now let's see the electron geometry. So you need to be little bit of check it out here, that which one is which angle. Now let's see take the red one. Okay. What does it angle? Linear, trigonal, tetrahedral, planar. So you know, here we have some angle. 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 So on the basis of the angle, we have different shape. Okay. So like here we have, like this is the, which one is the tetrahedral? I think this one. And we have like that trigonal planar 120, tetrahedral 109. Yeah, I think here we go. Linear 180, this one I think. Octahedral 90. So we have electron pair and the shape of the their structure planar and the bond angle. So the electron geometry of a molecule, that is the arrangement of electron in space, is attained by minimizing the pair. So when we draw, we try to be as far as can be. And this is some, and that are specific, fixed. Most of the compound come within these shapes. Electron pairs always spread themselves in three. Now also I want to tell you why I was telling. Let's see if I found it or not. I will show you, then you will understand. Three-dimensional rotation of methane, CH4, okay? See? This is how they wrote. So we have some software, we will write it and that will show and stable like that. So that means if this is this situation, we can calculate the angle and we can find out that which situation is most stable and good for the particular compound. It's interesting. If you have a ball and stick, you know, we play the Lego or different types of puzzle. So you can have this ball and stick. Which one is carbon? Which one is hydrogen? So you can make and you can rotate it like that. Oh, here we go. This guy show this one. See, this one I was talking. So this is how actually we can rotate, and but we have the angle for different types of shape and angle. See? This is the basic chemistry, so maybe we will not go detail, but when you will have the organic chemistry, you will have detail on that. So let's go back. So that's why we do the 360-degree rotation, so that we can keep apart the electron group as far as we can to avoid the repulsion, because they interfere their stability. Here, the another things I want to show you, the otherwise you will not. Axial and equatorial. This is called the conformation. So this is, don't scare it. You just need to be, I just need to show you what. So You know, when you are going to learn the structure, how to write the structure of organic compound or something, then you will see this type of bond. So when this, you know, A and equatorial E. So you will see here, draw this one. So when we will draw this type of three-dimensional structure or like that, we will put the hydrogen. So when you will see that some are the straight, that's called the axial, and some are like that, go on angular, that's called the equatorial position. Axial position and see equatorial position. So that also important in their stability, rotation, and the angle conformation. So electron pair can spread themselves, and this type of situation comes, and that contributes for their angle and the rotation. Finding molecular geometry. Draw the Lewis structure, determine the electron geometry, determine the molecular geometry, looking at only the atom at the, around the central atom. So in your job, what type of question can come? You don't have to go details. So you have to just learn that which one is linear called 180 degree. If you have already mathematics class in the high school, especially the higher mathematics, maybe you know about that. Do anybody had the higher mathematics in the high school or college? So then maybe you did the trigonometry. Did you ever do the trigonometry? Yeah, so you know the angle, correct? How? So you need to know that the which one is which angle and the name, so that you can identify if you give you any compound. Got it? Yeah, actually you guys don't have the detail. See? You just need to be identified. Now, the thing is that since you need to be apply your electron geometry, lone pair, and Lewis, so we have the another things by calculating. We can calculate that which one will be linear, which one will be trigonal on the basis of the lone pair. So now let's look into the this here. Zero lone pair linear. Trigonal 120, zero lone pair trigonal, and this is if the one lone pair, this is will be bending. Tetrahedral, as I said, the example show the methane 109.5. This will have the zero lone pair, one lone pair, and two. So this can be this way. And then the 120 trigonal bipyramidal, you will count from 0 to 3. Then octahedral 0 to 4. So you may need to little bit of look into here. So there are 5 distinct electron geometries. So the molecular geometry is found by looking at the electron geometry and counting the number of lone pairs. So how many lone pair you have? So you can guess what type of molecular geometry you have. The electron geometry and molecular geometry of a phosphorus trichloride molecules are, and so we can write, I think this is tri. Yeah, see, tetrahedral and tri. How you know? This is, since this is the trichloride, so I just visualize here the example. This is the penta, but if this is tri, it should be kind of like this type of. So you have to go through some practice question. The molecular geometry is a boron trifluoride molecule. I think it will be tri, but T shape here. Two lone pair T shape. So two lone pair T shape. So where it's going, let's find out. Go back to the two lone pair. Where the two lone pair T shape? Here is a 0, here is a 1. Okay, this is the exception one. See, because I don't see any table have the two lone pair. So this is the exception one. You guys need to know. T shape and trigonal pyramidal. Let's see. Oh, not this one. We are talking about this one. Yeah, two pair T shape. Yeah, that's a see. That's a, I always see. Here we don't have the T-shaped one. So this is the exception one. So please practice, and that's all. Oh, I think we have here this one something. We should recognize that lone pair electrons distort the bond angles, making them smaller. So what does it mean? Remember that lone pair of electron occupy more space than the, oh yeah, here is a one term called the electron cloud. So bulky electron. Bulky means we know the more space, taking the more space. So if you have the lone pair electron, they take the more space than the electron are shared in a bond. So that means here, so the space, the lone pair will take the more space than the electron that already make a bond. So we should recognize that lone pair of electrons distort the bond angles, making them smaller. So we have to find that. And that's all. Today we learn a lot. So practice it. If you have a time, I will suggest to practice today, then you will never forget. Because today's lecture, you don't need to memorize too many things. Okay? So if you practice, the math problem will be very and obviously you can go back to the recording.